Okay, so recording now. So I'm going to review chapter 17. There are some rather tricky topics in chapter 17. So let me get up the point. Okay, does everybody see the PowerPoint here? I need Kelly to answer me.
Yes, you're good.
Okay, so once again, you got to read the chat for me.
Yeah, absolutely.
All right, so the main idea to get across in this chapter is electric potential energy and electric potential. So my plan is to introduce the idea of electric potential that's measured in volts by doing an analogy with gravity. So there's two situations. One is which you have a uniform gravitational field or uniform electric field. And then the other situation is when you have a non-uniform gravity and non-uniform electric field. So I'll start with the uniform gravitational field. So this is like being near the surface of the Earth and having a mass there. So here's the ground. There's a mass. And so there's a force of gravity that acts on the mass. It points downward, and it's got a magnitude mg. Right, so a mass near the surface of the Earth has gravitational force acting on it. That points downward and has magnitude mg. Okay, so you know this from last semester. And you know that this is a very good approximation for heights above the ground that are very small compared to the radius of the Earth. So in this whole area, we have basically the same force no matter where we put the mass. Now let's think of that force as arising in two steps. Number one, first step, the point in space where the mass will be, so it's not there right now, but where the place where it will be has a vector g associated with it. So that's the gravitational field vector. It has magnitude g, which is 9.8 meters per second squared, and it points downward. Right? But it's not a force, right? In fact, it's an acceleration. But it's a force that you associate with a point in space, whether or not there's a mass there. And then when you do put a mass there, in some sense, if I'm going to anthropomorphize things, it senses the gravitational field and thus feels a force of magnitude mg that points in the same direction as that g vector. So then there's the force. Right, so the two parts are the point in space has a gravitational field vector because we're near the Earth. You put the mass there, it senses that and experiences the force. Right? So in this situation, the gravitational field vector is the same everywhere because I'm assuming that we have a uniform gravitational field. And now we know that g is in meters per second squared, but if you look at this formula, you can think of the units of g as just being newtons per kilogram. Right? If g has units of newtons per kilogram, you multiply by kilograms to get newtons. So it's appropriate to think about g having those units. And in fact, if you work out newtons per kilogram, that's the same as meters per second squared that we're more familiar with. So the gravitational field has units newtons per kilogram. And in fact, you can write this F equals mg with the vectors. That includes the magnitude and the direction information of the force in the gravitational field. Now, we only ever have positive mass. No such thing as negative mass. So the force and the gravitational field vector always point in the same direction. Okay, so I hope that's very clear, very familiar from last semester.
Yes.
The only kind of twist here is that I'm telling you that g has units of newtons per kilogram. All right, so let's now talk about the case of a uniform electric field. So how do you get a uniform electric field? You get two parallel plates that are very large, and in between them, you'll have a uniform electric field if they're charged. So here I'm assuming that the lower one has a negative charge, the upper one has a positive charge. Right? And really, the electric field is uniform towards the center, which is why I'm saying, imagine that these are really, really large, so that this electric field is uniform everywhere in the space in between. It's not towards the edges, it kind of bends out a little bit, but I'm going to ignore that. All right, so I drew electric field vector everywhere, just like I had a gravitational field vector everywhere above the Earth. Here's just one of them. If I put a charge in there, in that uniform electric field like this, here's a positive charge. Q is greater than 0. There's the electric field at the location where I put the charge. So in some sense, the charge will sense the presence of that electric field and feel the force. And the force is given by Q times E. So that's directly analogous to mg. Right? Instead of mass, I have the charge. And instead of the G vector, gravitational field vector, I have the electric field vector. Right? So it's the same. And notice, by the way, that I oriented the charge on my parallel plates here sort of so that they point down on the screen the same way gravity did. But there's no gravity in this case. This is just two charges here and ignoring gravity entirely. So there's no up or down, except sort of as you look at the screen. All right, so once again, in this situation, the electric field is the same everywhere between the plates. That's how we get the uniform field. And since F equals QE in magnitude here, you can think of the electric field as having units of newtons per coulomb. Same way the gravitational field was newtons per kilogram, except this time it's newtons per coulomb because we're talking about a charge. And that is the usual units for electric field that you'll find. And the equation here with the vector signs still holds even if the charge is negative. Remember, in the gravitational case, you don't have negative mass, so that force always points in the same direction as gravity, downward, as gravitational field vector. But in the case of charges, we have positive and negative charges. In this orientation, the way I drew things here, and I put the positive charge, the force is towards the negative plate, downwards. Remember, there's no gravity, but it's downwards, the way I drew it. But I could have put a negative charge there. And if I put a negative charge there, the force goes the other way. Right? And so if you look at this equation, if Q is negative, you see that the force vector and the electric field vector point in opposite directions the way they do here in this diagram. So that's one thing that's different between gravity and the electric field. You can have positive and negative charges, but you can only have positive masses. If you had a negative mass, it would fall upwards, up into the sky.
So he mentioned the negative thing about like throwing a rock up, and I had a really hard time following what that might mean. Is this really all you're saying? Is that if you had a negative charge, it's just that it would be reversed, which is something you can't really conceptualize with gravity, but in an electric field, it makes sense.
Yeah.
Okay.
Yeah, because in the case of gravity, masses are only ever positive. When you're talking about charges, you have positive and negative charges. So masses fall down, and meaning they spontaneously move in the direction of the gravitational field. And positive charges, if you let them go, will spontaneously go in the direction of the magnetic field, the electric field. But a negative charge will go spontaneously in the opposite direction opposite of the electric field.
Okay.
And that follows from this equation right here, or this one here. Right? If Q is positive, the force and the electric field point in the same direction. If Q is negative, the force and the electric field point in opposite directions. Okay?
Yep. Thank you very much.
Okay. All right, so we were talking about forces just now. We were talking about forces. Now let's talk about potential energy. And notice, by the way, that what we're going to do, we were talking about forces, which are vectors, and electric field is a vector. Now we're going to talk about potential energy, which is a scalar. It's measured in joules, and it doesn't have any direction, right? And we'll also talk about potential, which is also a scalar. All right, so go back to the gravitational field. Here's the surface of the Earth. Here's the mass. It's got this gravitational force acting on it that comes from the Earth. And all throughout space above here, we've got this gravitational field vector associated with every point in space. Now, if we're going to talk about potential energy, we need to say where the mass is. So we need a coordinate system. And also, so here's a coordinate system. Let's say up is positive. So this really is up because of the ground. I put the origin on the ground, and then calling the direction up, y. Mass at this location is at a location y equals h, so h for height. Because I put the origin on the ground, then this y coordinate of this mass is equal to the height above the ground. So that's why I'm calling it h. All right, but if we're talking about potential energy, we also have to say where zero gravitational potential energy is. We have to choose an origin for the potential energy. It's quite natural to put it on the ground. So I'm going to say that the altitude that corresponds to zero gravitational potential energy is that of the ground. So with this choice, then it's easy to say, oh, by the way, so yeah, here's my list of things. For this coordinate system, I put the origin on the ground, positive y is in the up direction, and zero gravitational potential energy is on the ground. So with those choices, the mass here has this much gravitational potential energy, mgh. H, remember, is the height above where we said the zero gravitational potential energy altitude is. In principle, H could be negative. I could put it underground, and it would have a negative value. But never mind that. You're familiar with this formula, I think. Okay, so now, once again, let's think about this arising in two steps. The fact that this mass in this gravitational field has this much gravitational potential energy. So two steps is, first of all, basically it's this. We put parentheses around the G and the H. This point in space, when the mass is not there yet, we'll have associated with it something called gravitational potential. So the word energy has been removed. It's just gravitational potential. It is a scalar quantity, and it's the GH part of this formula. So if you look at this formula, you see that quantity GH has units of joules per kilogram. Right? Multiply it by the kilograms of the mass, and then you get the joules. All right, so a point in space has associated with it gravitational potential, and the formula for it is GH. When you put the mass there at that point in space, it senses the gravitational potential and gets, in some sense, mgh, joules of potential energy. So what we did is we defined gravitational potential, which I'm writing as a V with a subscript grav, to be what's in parentheses here, the GH. And then in terms of this gravitational potential, the gravitational potential energy of that mass is the mass times the gravitational potential at that location in space. Okay, so it's a little strange kind of manipulation when you're talking about gravity. Nobody does this, but there's no reason you can't. Right? All I did is just separate out the GH part of this formula and give it a name, and then conceptualize it as some quantity associated with every point in space. So the gravitational potential given by that formula depends on the position of the mass, the height, right, in space. So here are two places, A and B. Which one of these has more gravitational potential, A or B? Somebody say, A. Somebody give an answer.
A. We're all saying A.
Yeah, everybody's saying A. Yeah, exactly, because the H is higher. The height of, the Y coordinate of position A is bigger than the Y coordinate of position B. So more gravitational potential up there. Now notice that when something falls, if I put a mass at location A and let it go, it falls, and it moves towards lower gravitational potential. In so doing, it loses gravitational potential energy. Okay. All right, so I hope that's familiar because it's gravity, and maybe a little awkward because of the strange things that we're defining. Nobody does it in terms of gravity, but they do it in terms of electricity, electric fields and things. So let's work that out now. Oh, by the way, here it is. Yes. Yeah, potential energy is m times the electric or gravitational potential. So let's now do that with the electric field. So that was gravitational potential energy. Let's talk about electric potential energy now. So once again, we want to talk about a uniform electric field. So we've got the two parallel plates with a uniform electric field in between. And I put a charge there, which is positive. Once again, we're talking about potential energy, so we have to use a coordinate system. Excuse me. And we need to say where 0, and that should say GPE, but EPE, electric potential energy. So here's my coordinate system. I'm going to put the origin, where's my pointer? There we go. I'm going to put the origin of the coordinate system on the surface of the negatively charged plate. And I'm going to draw the positive direction as pointing towards the positively charged plate. Notice, by the way, that the location of the positively charged plate is the distance d away. So I've given this coordinate d. And the coordinate of the charge is y. And I put a little subscript I here, just to make it different from that y. So y sub I is the coordinate of the charge. Okay, see how I set things up? Now I need to say where 0, here it says GPE again, I should say EPE. So I need to specify where 0 electric potential energy is, and there it is. So I'm going to put it on the surface of the negatively charged electrode to coincide with the 0 of my coordinate system. Right? So far, it looks just like gravity, except that remember, there's no real up or down in this case, because I'm talking about two parallel plates and I'm ignoring gravity. But I have a positive direction from the negative to the positive, and I put the 0 of both the origin and the electric potential energy to coincide with the surface of the negatively charged plate. This is basically what I just said. The upper plate is at location y equals d, capital D. All right? You can interrupt me if you have any questions.
We're good.
The charge, yeah, go ahead.
No, I was just saying we're good so far.
We're good. All right. The charge Q that I've placed here has electric potential energy given by this formula. Q times E times the coordinate yi. That looks just like MGH, except that the mass has been replaced with a charge. The G, the gravitational field, has been replaced with the magnitude of the electric field here. And the coordinate is the yi. It was H before, but it was the y coordinate of the mass. And here I've just labeled it as yi. See how they're the same thing?
Yes.
Okay, so once again, we're going to think about this arising in 2 steps. So notice I took the charge away. And basically, once again, it corresponds to putting parentheses around this part of the formula, the EYI part. So number 1, the point in space here, see it's an open circle, there's no mass, there's no charge there yet. That point in space where the mass will be will have an electric potential associated with it. And it's a scalar quantity, it's not a vector. And it's this part of the formula. It is EYI. Notice that it has units of joules per coulomb. And multiply this by the coulombs of the Q, and you'll get the joules of the electric potential energy. Joules per coulomb have a name, and they're called volts. These are the same volts as you see on a battery, right? The battery gives you 9 volts. These are the same volts. This is what volts are. Joules per coulomb. Now, when you put the charge Q at that location, and it should have turned full, all right, but I'm going to imagine putting a charge Q here. It will, in quotes, sense the electric potential and get this much potential energy, this many joules of potential energy. And so we're going to define the electric potential to be what's in parentheses here, EYI, so electric field times the position. And in terms of that, the electric potential energy is Q times V. That's for a charge placed at a location that has the electric potential V. And so this is what you see when you're talking about electricity. And I've drawn the analogy with gravity so that maybe you can understand the steps a little better. You don't do this in gravity, you just stick with this formula. But in electric field, electric stuff, you do use this formula a lot. Okay? So here's the analogy. I've got uniform, and the key word here is uniform. We're going to talk about non-uniform in a minute. But for uniform gravitational field, uniform electric field, we've got G and E as vectors. For the force, we just multiply it by a mass or multiply it by a charge. Remembering that Q could be positive or negative. M is only ever positive. For potential energy, mgh, or QE, and then coordinate y. So in order to make sense of what h means, you need to say what your coordinate system is, so you can measure the height. In order to make sense of what y means, you need a coordinate system, so you can say what the y coordinate is of the charge. Electric potential is just the GH part of that, and it's just the EY part of that. Once again, you need a coordinate system to make sense of what the H means, and you need a coordinate system to make sense of what the Y means. So then, potential energy written once again in terms of that is just M times V grab, which you never use, but electric potential energy is charge times voltage. You see this all the time. This is always positive, charge is positive or negative. Everybody still with me?
Very much so.
Okay. Good. I only heard one ding though. Where's everybody else?
They're here.
Engagement, people, engagement. Okay, there we go. There we go. It's nice to know that people are out there because I'm just in a room talking to a laptop. As are you. You're listening to one. Okay, thank you.
Really
brief summary of
I think you made a lot of our lecture from the other day make more sense. So that, which is mostly the point of recitation, but that is greatly appreciated.
Okay, very good. I'm glad. All right, so here's a brief slide of what you should know about the case of a uniform electric field. Again, you make a uniform electric field with two large parallel plates. The field is uniform just in the central portion of that, away from the edges. Set up a coordinate system and pick a 0 for your electric potential energy. I like to put the origin of the coordinate system and the 0 of the electric potential energy on the negative plate and have the positive direction be towards the positively charged plate. I just like that. You don't have to do that, but I like that. The electric potential at position yi, given the coordinate system, is electric field times yi. It's a scalar quantity. It's measured in volts. It has no direction. It's a property of a point in space where there's an electric field. If you put a charge Q at that position, it will have electric potential energy equal to Q times the voltage of that point in space. And that's in joules. Right, so coulombs times joules, coulombs times volts is joules. Because volts are joules per coulomb. Okay, so this formula, sometimes you see with little deltas in front of them, in front of the U and in front of the V. So you could say that the magnitude of the electric field between two large charged parallel plates like this that are separated by a distance capital D, as you can see here by the coordinate system, using this formula, this one here, you can relate the voltage across the two plates and the electric field just by using this formula. Voltage is the electric field and then times the distance, right? If I put the 0 voltage down here, then the upper plate is at voltage V. So the electric field has a magnitude V divided by D. And that's uniform everywhere in between. All right, so let me say that again. What I want to do is I want to relate the voltage between two parallel plates, by which I mean if I put 0 on one of the plates, say the negative one, then the other plate is at a voltage V. Okay, so then V is related to D and E this way. E is the electric field strength in between. So you could solve it and write it this way. If you look in the book, there are these negative signs floating around, which confuses everybody. So what I recommend is using this formula here with absolute values, and then determine the direction of the electric field by just looking at where the charges are. Remember, the electric field direction is specified by the direction in which a positive test charge would move. If I were to put a positive charge here, it would go towards the negative plate and get pushed away from the positive plate. So that's why the electric field points this way. So use this formula for the magnitude part, and then look at the picture and where the charges are to figure out the direction of the electric field.
I think you should rewrite the book. Because that
I don't get paid enough, I guess.
So much easier to specify instead of dealing with all the negatives, because, and Will agrees with me, because it's just like this makes a lot more sense, and then following whichever way the charge would go based on where like the electric field points, like, or the where the positive is. That makes way more sense. And
good, I'm glad. The book is not wrong. I mean, those negative signs are what lead to all these formulas.
No, it's not wrong at all. It's just
when you distill it, you don't need those details.
Right, and I think it, I don't know if they use the same book for the university physics, but I imagine they don't, because I imagine there's a lot more calculus based on that. But I think that this would be easier for a lot more people to follow, and then specify with what you just said. So anyway, totally off point.
All right, I'm glad it's helpful. Unfortunately, we don't have much time, so let me keep going. But interrupt me if there are questions. Kelly will tell me that you're there. All right, so we just had this formula here that the electric potential is electric field times the position, right? Which is like gravitational potential is G times H, kind of. Here's the same diagram that I've been showing you. I put V equals 0 down here. That's just a different way of writing 0 EPE, right? And up here, the voltage is E times D. Just using this formula and plugging in the coordinate of that position. It's positive, the way I've written it here. If I put a positive charge here, the force will be this way. So notice that a positive charge falls. If I were to let it go, it would move this way. It falls. Again, it's in quotes because there's no up or down, really, because it's just these plates. But if I let it go, it's going to move in that direction. So in that sense, it falls towards the lower electric potential. This is at higher voltage because E is positive and D is positive. So if I let it go, it falls towards lower voltage. Here's the same situation, but I'm going to put a negative charge there. It'll feel a force upwards, right? The force is Q times E. Negative makes that force point in the opposite direction of the E. And if I let it go, it's going to fall upwards, meaning in that positive direction, towards higher voltage. So positive charges spontaneously want to move towards lower voltage. Negative charges spontaneously want to move towards higher voltages.
Dr. Barreto?
Yes, go ahead.
I have a quick question. So from chapter 16, it talked about how positive charges point away from the electric field, and then negative
Wait,
charges.
hold on. Let me back you up there. Charges don't point.
Okay.
So what do you mean by that?
I guess the force on the charge points.
Okay, the force that acts on a charge
The force
points in the same direction as the electric field if it's a positive charge.
I thought it was for a negative charge. No? Okay. All right, thank you.
I'm going to write something here. So force is QE. So you can see that if Q is positive, the force and the electric field point in the same direction, as you can see here. If Q is negative, the force and the electric field point in opposite directions, as you see here.
That's
You see that, Julia?
Yes, I do. Thank you.
Okay. So that's true. And what I want to point out is that the way things are set up here, the upper plate is at higher voltage in both cases, right? Because that's a property of a location in space. So positive charges fall, spontaneously want to move towards lower electric potential, lower voltages. And negative charges spontaneously want to move towards higher voltages. They kind of fall upwards, if you will. But in both cases, they fall towards lower electric potential energy. So falling means you lose potential energy. In both cases, you lose potential energy. In this case, the voltage of the position where the thing is decreases. So therefore, the electric potential energy decreases. In this case, the voltage at this location is positive, but the charge is negative. So you're starting out with a negative electric potential energy. And it's going to go towards increased voltage. But since the Q is negative, that means you're going to get even more negative for the electric potential energy. And so this guy has negative electric potential energy, and as it falls, it's going to get even more negative. This guy has positive electric potential energy, but as it falls, it's going to get smaller. Okay? A little tricky to keep track of all these things, but here's your little cheat sheet. Positive charges fall towards lower voltages and lower electric potential energy. Negative charges fall towards higher voltages, but lower potential energies. Okay.
Okay, we're with you. We're engaged. We're with you.
Good. We need to move on. We're running out of time. Non-uniform fields. So now let's talk about, instead of a uniform field, a non-uniform field. So I'm going to skip the gravity part because I don't have time. But let's consider an isolated charge. An isolated and fixed point charge, capital Q. Here it is. The electric field around it is not uniform. Right? Instead, we had this formula from last week. Remember this? And I put magnitudes, symbols, absolute value symbols, so that I'm only talking about the magnitudes. And notice that it depends on the radius. R is the distance away. So here's the point in space, the distance R away from the charge Q that's fixed in space. The electric field at that location has this magnitude, KQ over R squared. And in this case, that's positive. And the R is positive, so everything is positive. The direction of the electric field is determined by the direction of the force that would be felt by a positive charge if you were to put it here. So imagine putting a positive charge here. It would be repelled from this guy. So the force would be towards the right, and that's why the electric field points to the right. But really, my point is that it depends on the radius. The farther away you are, the bigger the radius in the denominator here is, and so the smaller the electric field is. All right, so now let's put a charge at that location, charge little q. Question is, how much electric potential energy does that charge have if it's placed near this fixed charge, capital Q? At a distance r from that point charge, capital Q, the charge little q has this much electric potential energy. I assume you've seen this. There is a gravitational analog, but I don't think we spent very much time on it last semester.
Yeah, that would be
So
the big G, and then
the big G, M1, M2, and then R.
Yeah.
Notice that it's not an R squared.
Yes.
So that this is the electric potential energy of this situation. So you can think of it as the electric potential energy that Q has because it's in the presence of big Q. And again, remember that the R in the denominator is not squared, but the units work out. Now you might say, where is the zero of the electric potential energy? And the answer is it's kind of built into this formula. If you use this formula, you're using the assumption that as R goes to infinity, you're going to get zero for the electric potential energy. So built into this formula is the assumption that zero electric potential energy is infinitely far away. You can see that with the formula, right? If R gets really, really large, the electric potential energy gets smaller and smaller and smaller. So if you use this formula, you don't get to pick where zero electric potential energy is. It is infinitely far away. In other words, that's built in. It says here, zero electric potential energy is infinitely far away by definition for this formula. All right, so this is what I just told you. Here's the charge Q. Here, let's say I put a positive charge, location R away from it, positive charge little q. And what I want to draw is a graph of the electric potential energy of that little charge Q due to the fact that it's near the big charge, capital Q. And then I'll move it back and forth and graph it. So that formula, as you can see, everything is positive in this case. The two charges are positive, the distance is positive, the K is positive. So the closer I get, the smaller the R is, and so the bigger the electric potential energy is. It's like I'm pushing something uphill. If I bring in charge Q, which is positive from infinity, you're storing energy in it in the same way that if you roll a ball up a hill, you're storing gravitational potential energy in it. You can think of the shape of this curve as actual hill. You're standing here and you push the charge up and it goes up. So you're storing energy in its location by pushing it up. And you can see that you'd have to push hard because it's repelled by the charge, by the big Q. If you were to let it go, it would fall, and it would move towards lower potential energy. Remember, the big Q is fixed, so if I let go of little q, it's going to fly off to the right, or it's going to roll down this hill towards larger and larger values of R. Now, if I put a negative charge there, it will be attracted to the fixed big Q charge, which is positive. So the graph of the electric potential energy looks like this, right? The little q is negative, everything else is positive, so the overall thing is negative. The graph looks like this. Here's the origin. And so it's like a hill if you're walking down a hill. If you bring in a charge from infinity, you give up potential energy, as if you were taking a ball and moving it go downhill. If you let it go, it will fall in. It will be attracted to the big Q charge, which is positive, spontaneously move in, and so move towards lower electric potential energy. And so you see, getting closer means you go to more negative values of the electric potential energy. Okay? So that's kind of a curious fact that you have, that follows because you have positive and negative charges. Now let's talk about voltage. So this is what I just told you about the electric potential energy. For the voltage, we basically factor out the charge that you're going to put at some point in space. I just separated the little q here, and what's inside the parentheses is what I'm going to call the voltage. So at a distance r from an isolated point charge, capital Q, a point in space, remember it's a property of the point in space, has in volts this many volts, kq over r. And q is the big q charge, right, that we're near. And once again, zero voltage is located infinitely far away. That's a definition that's built into this formula.
I have a clarification question. So the big Q is the overall charge of what you're looking at. The little q is like the point at where you are. Like if you had, like, yes, okay, yep, it's right there.
There.
Yes, okay.
Big Q is fixed in space, and because of that, everywhere in space around it has electric potential associated with a certain number of volts.
Okay.
The same way, if I'm near a planet, Every point in space has a gravitational field vector. Even if I don't put mass there, there's a G.
Okay.
And it's non-uniform because we're not, we're talking about big distances. So this is what I just told you. At a distance r away from an isolated point charge q, point in space has this many volts of electric potential. Built into that is the definition that 0 volts is infinitely far away. So near an isolated positive charge, the voltage is positive. Graph looks like this. K is positive, R is positive, Q is positive. The closer you get, the higher the voltage is. The electric field, remember, to figure out the direction of the electric field, you imagine putting a positive charge here. It would be repelled from this one, so the direction of the electric field is away. It points towards lower voltage. If I put a positive charge there, it would feel a force in the same direction as the electric field, away from the, in other words, towards lower voltage, as you can see. So positive charges, once again, fall towards lower voltage. Put a negative charge there, it'll feel a force opposite in direction of the electric field, in other words, towards the positive charge, right? That negative will be attracted to it. So negative charges will fall towards higher voltages, as you can see. Voltage is the property of the point of space. Forces and things are properties of putting the charge there and it feeling the field, feeling the electric potential. For a negative charge, the voltage is negative. Like this, right? The formula has a negative value for Q, see it's negative. Everything else is positive, so when you graph it, it looks like this. The closer you get, the more negative the electric potential is. Right? More negative volts, the closer you are. So again, the electric field points in the direction that a positive test charge would feel. In other words, it would be attracted, so to the left. If I put a positive charge there, that's the direction of the force, and it would fall towards lower voltages. The closer you get to the negative charge, the lower the voltage is, so it'll fall in that direction. The negative charge will fall towards higher voltages. This voltage here is negative, and farther away it gets smaller in magnitude, right? So higher voltage. You can see on the graph here. Okay, so I know that this can get confusing with all the positives and negatives and things, but I hope that was helpful. That was it for the slides. We have 5 minutes. Let me do a problem. I'm going to keep that notation. Let me do a quick problem because I think it's important to bring the ideas together. His mind is blown, I see. All right. All right, so
it just makes so much sense. So my mind is just kind of blown because it's just, when you look at it that way, it's just sort of obvious. That, I don't know if that's the right way to put it, but
the thing about physics is that, if it's presented to you and it feels obvious, when you go to do a problem, it's hard. You don't know what to do, which is why it's important for you to do this problem. Yes, that's very true for physics.
So much. If I had an essay exam about this, it would be so much easier than having to actually like.
All right, quickly, I've only got a few minutes. So here's a charge. Here's a question. You can magnify it with your little tool here. I think I cannot do it for you. In fact, it's not working for me. Here we go. Do you see it? Can you read it, everybody?
Yes.
It says a proton is accelerated from rest through a potential difference v sub 0. And it'll gain a speed little v 0. All right, so you put a proton at rest in an electric field. And so it'll feel a force and it'll accelerate and it'll gain a certain speed after going through this potential difference. If it were accelerated through a potential difference of twice as much, how much speed would it gain? All right, so I want to do that quickly. And I'll post more solutions, but here's this one in particular. Okay, so zoom in as you wish so you can see. So I drew here. Do you see my finger pointing? Okay. So
Yeah.
I drew here a direction in space, x. And I'm going to say that the positive charge, which I drew here, starts at this position I'm calling I for initial, and it goes to position F for final. I place it at I, and it spontaneously moves towards F, right? Because there's electric field of like a potential difference. I'm going to say that the voltage at location I is VI, and the voltage at location F is VF. Now it's a positive charge, so I know that it's going to fall towards lower voltages. So therefore I know that VI is bigger than VF, so that I wrote here. VI is a higher voltage, VF is a lower voltage. Right? So to figure out how fast it's going when it gets to F, we just do conservation of energy. And we'll use this formula here, that the potential energy is Q times V. Kinetic energy is 1/2 mv squared. And I'm going to point out that my V for velocity is the squiggly one, and my V for volts is the big capital one with the straight sides. So this is a conservation of energy problem. In my initial situation, what is my energy? It's kinetic energy plus potential energy. No kinetic energy because it's not moving. And then the potential energy at this location is the charge Q times the voltage at that location. That's what this formula here says. In the final situation, the energy is, again, kinetic energy plus potential energy. It is moving, so it does have kinetic energy, 1/2 m squiggly V squared. And then the electric potential energy is the charge times the voltage at that location. So Q times VF, again, using this formula. So do conservation of energy. Set these things equal to each other. EI equals EF. So Q VI equals 1/2 mv squared plus Q VF. Then all I did is move the VF to the other side and factor out the Q. The problem tells me that the potential difference between the two locations is V0. So that means that this in parentheses, VI minus VF, is what V0 is. So I replace the VI minus VF with V0. And then I can solve the equation for squiggly V, which is the speed. The answer is square root of 2 times Q V0 over M. So I don't like this problem the way it's worded because it just tells you that the potential difference is V0. What it does not tell you is whether the potential energy increased or decreased, right? Whether the potential difference is positive or negative. There's enough information to conclude that, however, because we know it's a positive charge, to tell you it's a positive charge, and it spontaneously went from the initial to the final position. We know positive charges fall to lower voltages, so we know that it decreased in voltage. Yeah, I'm out of time. So you're welcome, Vincent and everybody else. I'm done. I'm going to post these solutions, including a handful of other problems. And I have an office hour Friday, 4 o'clock. Look for the Zoom link. If you don't get it by email, go into Blackboard. It'll be posted in the announcements section of the Blackboard for this class. Okay. Have a good day, everybody. Maybe see you tomorrow.
Thank you.
You're welcome. Bye, everybody.
Thank you so much. Have a great day.
Oh shoot, I didn't write them. Oh, wait, don't go, no, don't go. I have to take a screenshot. Don't go. Right, people are leaving. Darn it. Oh, I have a recording. I know where everybody is. Okay, screenshots taken. Stop sharing. Stop the recording.